Hari Om girls. So in the operating system course, we are currently discussing module 2. These are the different topics of module 2. We had already talked about the process concept, in which we discussed what do you mean by a process and what are the contents of a particular process, what are the things that are included in a process like program counter, stack, data section, heap, which will be available in the primary memory of the computer system. Then we talked about the life cycle of a process, where it takes different states or it changes different states during the life cycle of a process. Now when I say lifetime of a process or a life cycle of a process, it starts with the new state and it will go into the terminated state when it completes its execution. These are the different states, and the diagrammatic representation of different process states was also discussed. Then we talked about the process control block, which is very important. Whenever the CPU takes a process for execution, it creates a process control block which stores the information about the process. What is the current status of a process, that will be stored in the process control block. So it will have the process ID, or you call it as process number, then what is the content of the program counter and all the CPU registers which were used by the process. Then it will also have the scheduling information. It will have the process state, in which particular state, whether it is in the waiting state or is it in the ready state, that information will also be stored. And it will also have some accounting information as well as input output status information. And not only that, we had also discussed how the CPU will switch from one process to another process with this particular diagram. And this diagram shows how the CPU will switch from one process to another process by the time how it is saving the state information of a particular process, and how does it load the state information of another process while switching from one process to another process. So these are the different information which will be stored in the process control block. Now today we are going to talk about the process scheduling, which is very important. Actually, we will be talking about the different scheduling algorithms and how these scheduling algorithms differ from one mechanism to another mechanism, or one technique to another technique. All those things we will be discussing in detail. And this process scheduling is a very brief overview about the scheduling of different processes. Now, you know that process scheduling module is very important when the system has the capability to multi-program or multi-process. Because if it is going to be a single programming environment, scheduling is not at all required, right? It is not required. Why? Because all the resources, whatever resources are currently available in the system, say for example, the resource like CPU, the resource like memory, the resource like input output device, all these resources can be allocated to that particular program, because we are using only one program in the system. So if you have only one program running in the system, no problem at all, because all the resources can be allocated to the program. But the problem is, if we have multiple programs or multiple processes which are to be executed, then the resource allocation is to be carried out with proper allocation mechanism. Why? Because more than one programs will be requesting for the resource, or more than one processes will be requesting for the resource. Say for example, I have program 1 and program 2. Both the programs are requesting for the printer, or both the programs are requesting for the memory, right? So by the time the memory is to be partitioned in such a way that process 1 as well as process 2 are loaded into the primary memory at the same time. If this is the case, you need proper allocation mechanism. Correct. Now, the main objective of multi-programming, why we want multi-programming, right? So it is to have some process running at all times. What do you mean by that? Suppose I have process 1 and process 2. If process 1 is doing some input-output operation, by the time CPU is going to be idle. So to utilize that idle time, what we can do, we can allocate process 2 also into the CPU so that you maximize the CPU utilization. So this is one of the very main objective of multi-programming. We can have the CPU utilized at all times so that more than one process will be running in the CPU. Or if you take the time sharing environment, right? So there are different environments available for running more than one programs. One environment is multi-programming environment. Another one is called as time sharing environment. Now what is the objective of time sharing? It is to switch the CPU among processes so frequently, right? So you are going to switch from one process to another process so that the users can interact with each program. Now, when I say the users can switch from one program to another program, since the process switching is very fast, it will be done in nanoseconds or in microseconds, the users may not be able to understand which program is currently executed by the CPU because it is so fast, and the user will feel that all the programs are running simultaneously by the CPU. So that is one of the main objective of time sharing environment. So whether we have multi-programming or time sharing or multi-processing, whatever environment we are going to have, all these environments will be executing the programs in more than, will be executing the programs simultaneously, or I can say concurrently. Now the question is, if we have concurrent processes or simultaneous processes, obviously we need a manager called process scheduler, and this scheduler will select any one of the processes from the list of ready processes, because I am having 3 programs ready now. Say for example, I have my media player, I have my Microsoft Word processor, and at the same time I have my web browser also, right? I'm just talking about the 3 common applications which you always open in your laptop or in your desktop, right? So you will have a web browser, obviously, if you want to browse through. And the second one, obviously you may be preparing some document or you may be preparing some PowerPoint presentation. If so, you will have that particular application also open. And by the time, suppose if you want to listen to the music and work, obviously you will have your media player running. Now imagine all the 3 processes are initiated, all the 3 applications are initiated. So 3 processes are now ready for execution. If this is the case, only one process can be selected from the list, and the process scheduler is the one which will decide which program can be executed now by the CPU. That is the point to be noted here. Now, as I told you, the process scheduler is going to select one process from the list of ready processes, right? So obviously the process scheduling mechanism is using a queuing technique for managing all the processes, because I am having more than one process. Ella process ni orimichittu I cannot give it to the processor. So you need someone to manage the processor as well as all the running process. Who will be managing it? The scheduler will be managing. How the scheduler is going to manage? That scheduler will use the queuing technique. Now let us see what are the different queues available for scheduling. We have a job queue, we have a ready queue, we have a device queue also, right? So these are the three different queues which will be used by the scheduler for managing all the processes. So let us see what is a job queue. So job queue will contain all the processes whichever is available in the system, right? So whatever process you have initiated, you might have initiated lots of background processes, you might have initiated lots of foreground processes. As I told now, the example, the web browser application you have opened a media player, you have opened your word processor also. So that means all these processes will be available in the job queue because they are all initiated by your system. So all these processes will be available in the job queue. Now what is the next queue? Ready queue. Now this ready queue will have the set of all processes residing in the primary memory, and it is ready and waiting to get executed. This is the ready queue. And this is always stored in as a linked list. Obviously you have studied linked list, doubly linked list, circular linked list. That is all the data structure which is used for the queuing technique. And here we are going to use a singly linked list which will be acting as a ready queue. So job queue will contain all the processes that are available in the system, whereas ready queue will have the processes whichever is currently available in the main memory and whichever is ready and waiting to be executed by the process. So processor vannitte ഏതൊക്കെ പ്രോസസ്സിനെയാണ് processor execute ചെയ്യാൻ പോകുന്നു ആ പ്രോസസ്സ് എല്ലാം റെഡി ക്യൂലാണ് ഉണ്ടാവുക. സോ ദാറ്റ് CPU ഫ്രീ ആവുമ്പം എന്താ ചെയ്യുക, റെഡി ക്യൂ എന്നുണ്ടായിട്ട് you can give it to the CPU. That is the purpose of having ready queue. You must understand the difference between job queue and ready queue. Job queue പറയുന്നത് whatever process is initiated by the system, all the processes will be available in the job queue, correct? Then it will enter into the ready queue. എപ്പോഴാണ് ready queue ലേക്ക് enter ചെയ്യുക? If it is ready, എല്ലാ initialization, linking, loading, everything is completed and now it is ready for execution. അങ്ങനത്തെ ഒരു സ്റ്റേജിൽ വരുമ്പോഴാണ് it will be pushed into the ready queue. Then you have another queue called as device queues. The list of processes waiting for a particular input-output device is called a device queue, or the set of processes waiting for an input-output device. So each device will have its own device queue. Say for example, you have a printer queue. What are the processes waiting for the printer? All these things will be available in the printer device queue. What are the processes waiting for the plotter? Then all the processes waiting for the plotter will be available in the plotter device queue. Or if any other device is some signal receiver or kind of like LED display kind of or you have fingerprint scanner. So all these devices will have its own device queue. So whichever process is waiting for the input output operation of that particular device will be stored in the device queue. Okay, so you must understand for each device we are going to have one device queue. Now if this is the case, you can observe here how the ready queue and the other various input output device queues are arranged in a system, right? So this is the diagrammatic representation of the ready queue and various input output device queues. Okay, so please observe this diagram, and in this diagram you have the queue header, and each queue is having a head part as well as the tail part. Head will be pointing to the first process in the queue. Tail will be pointing to the last process in the queue. Please make a note of it. In the ready queue, you will have a queue header. For all the queues for that matter, for all the queues you will have a queue header, and this queue header contains pointers to the first process control block and the last process control block. So first process control block will be pointed by the head pointer, and the last process control block will be pointed by the tail pointer. Now if you observe here, I have process control block 7, which is the first process control block. So head is pointing to this, and process control block 2, that means second process in the process control block on it. Seventh process in the process control block on it. Okay. Now the tail pointer is pointing to the last process control block. And you can see here, since it is a singly linked list, each process control block has a pointer field. This is a pointer field pointing to the next process control block in the ready queue. This is a pointer field in the process control block which is pointing to the next process control block in the ready queue. So linked list il ningalku next ennu paranjittulla oru pointer eppozhum undavum ille. നമ്മൾ നോഡ് ക്രിയേറ്റ് ചെയ്യുമ്പം ആ നോഡിൻ്റെ അതേ ഡേറ്റ സ്ട്രക്ചർ വെച്ചിട്ട് ഒരു പോയിന്ററും കൂടി ക്രിയേറ്റ് ചെയ്യും. ദാറ്റ് പോയിന്റർ വിൽ ബി പോയിന്റിംഗ് ടു ദ നെക്സ്റ്റ് നോഡ്. സോ ഹിയർ ദ നോഡ്സ് ആർ പ്രോസസ് കൺട്രോൾ ബ്ലോക്സ്. ദീസ് ആർ ദ നോഡ്സ് and each node will be pointing to the next process control block in the queue. Okay, and you can observe here, since PCB2 is the last process control block, and this pointer is having a null value, and you can just recollect the points of linked list data structure. Linked list data structure always the last node will be having a null pointer, right? So this is what is shown here. This is having a null pointer. That is why the tail pointer is pointing to this particular process control block, right? And apart from this ready queue, what will be the content of the ready queue? All the set of processes which are ready and waiting to be executed is now stored in the ready queue. Now apart from that, as I told you, various input output device queues will also be there. So you can observe I have a queue for magnetic tape 0 and another queue for magnetic tape 1 and another queue for hard disk and another queue for terminal, right? Different queues for different input output devices. So whenever a process is allocated the CPU, it executes for a while and eventually it quits and is interrupted or waits for the occurrence of a particular event, such as the completion of an input output request. Okay, I repeat, whenever a process is allocated to the CPU, right? For example, PCB is now ready and the CPU is idle nu paranjittundengal endha cheyva, from the ready queue process 7 will be allocated to the CPU. And CPU will be executing 7th process for a while. Korchu time it will be executed. And then suppose if there is an interrupt or if there is some input output operation coming in, obviously what it will do, it will be removing the process from the CPU and it will be stored in the corresponding queue. For example, process 7, let us assume process 7 എന്തിനാണ് ഇത് നമ്മൾ അലക്കേറ്റ് ചെയ്തു, അത് സി പി യുയിലേക്ക് അലക്കേറ്റ് ചെയ്തു. ദിസ് പ്രോസസ് ഈസ് അലക്കേറ്റഡ് ടു ദ സി പി യു. ബൈ ദ ടൈം ദിസ് പ്രോസസ് വാണ്ട്സ് ടു റീഡ് സം കണ്ടൻറ്റ് ഫ്രം ദ ഹാർഡ് ഡിസ്ക് എന്നുണ്ടായിട്ട് റീഡ് ചെയ്യണം, റൈറ്റ്? ഇഫ് ഇറ്റ് ഈസ് able to read the content. So while it is reading the content from the disk, the process will switch from the ready queue to the wait queue like po. Wait queue like endana ponu, because it needs this process to be completing the input output operation. What is the input output operation now? It wants to read the data from the hard disk, right? So this is what you have to understand in this particular diagram. Whatever processes are ready and waiting for the CPU, all these things will be coming into the ready queue. And if any process wants the input output operation to be completed, that process will be moved to the device queue. The process nu paranjittunga inde process control block aanu. Process control block will be moved to that particular queue, device queue. Okay, so now you can see that the representation of process scheduling is a queuing diagram, right? So this one we had seen what are the different queues available. Now let us see how the queuing mechanism is used for process scheduling. So this is the diagrammatic representation of process scheduling, which does the queuing process. So this is the one which is doing the queuing process. Now you can observe here, you have the ready queue. Ready queue is already shown in this particular diagram, right? So ready queue is shown, all the input output device queue is also shown here. Okay, so that queue is now represented here. You have a ready queue and you have input output device queue, and you have other squares also. You can see each rectangular box represents a queue. 1, 2, 3, 4, 5, 6. 5 queues are there. Okay. Then two types of queues are present, ready queue and the device queue. So this is the ready queue and these are the device queues available. And the circles here represent the resources. This is one resource, this is another this one is one resource, input output device, and CPU is another resource. Okay. Now the arrows indicate the flow of process in the system, how it is flowing from one queue to another queue, that is also represented here. Now imagine a process is in the ready queue. Now since it is in the ready queue, when the CPU is idle, CPU is now idle, you are going to push the process from the ready queue to the CPU, and CPU is currently executing the process. Okay. ഒരു പ്രോസസ് 1 എന്നുള്ളത് നിങ്ങളുടെ ഏതെങ്കിലും ഒരു സി പ്രോഗ്രാം എടുത്തോളൂ, ഒരു മാട്രിക്സ് മൾട്ടിപ്ലിക്കേഷൻ പ്രോഗ്രാം ഉണ്ട്, അല്ലെങ്കിൽ എനി അതർ ആപ്ലിക്കേഷൻ പ്രോഗ്രാം, നിങ്ങളുടെ ഒരു പൈത്തൺ പ്രോഗ്രാം, ഓർ യു ടേക്ക് യുവർ JDBC പ്രോഗ്രാം, എനി വൺ പ്രോഗ്രാം യു ആർ ഗോയിങ് ടു എക്സിക്യൂട്ട് ഇൻ ദ CPU. Now JDBC program you want to read a database or you want to read the data from the user. അങ്ങനെ യൂസറിനോട് പറയുന്ന സ്റ്റുഡൻറ്റിൻ്റെ നെയിമും റോൾ നമ്പറും ഒക്കെ ടൈപ്പ് ചെയ്യാൻ വേണ്ടിയിട്ടുള്ള പ്രോഗ്രാം കോഡ് വരുന്നുണ്ട് വിചാരിക്കുക. അപ്പോൾ when the user is typing the student name and roll number, by the time the CPU will push that process into the input output request queue, because input output operation is to be carried out. അപ്പോൾ ഇൻപുട്ട് ഔട്ട്പുട്ട് റിക്വസ്റ്റ് ഏതിനാണ്? കീബോർഡിലേക്കാണ് വന്നിട്ടുള്ളത്. കീബോർഡിൽ നിന്നുണ്ടായിട്ട് യൂസർ ഹാസ് ടു റീഡ് ദ ഡേറ്റ ഫ്രം ദ കീബോർഡ്. അപ്പോൾ ഓബ്വിയസ്ലി ഫ്രം ദ ഇൻപുട്ട് ഔട്ട്പുട്ട് റിക്വസ്റ്റ് ക്യൂ ഇറ്റ് എൻറ്റേഴ്സ് ഇൻ ടു ഇൻപുട്ട് ഔട്ട്പുട്ട് ക്യൂ. ഇൻപുട്ട് ഔട്ട്പുട്ട് ക്യൂ എന്ന് പറഞ്ഞിട്ടുണ്ടെങ്കിൽ ഏത് ക്യൂയിലേക്കാണ് പോവുക? വി ഹാവ് ഡിഫറെൻറ്റ് ഡിവൈസസ്. കീബോർഡിൻ്റെ ഒരു ഡിവൈസ് ക്യൂ ഉണ്ടാവും, മൗസിൻ്റെ ഡിവൈസ് ക്യൂ ഉണ്ടാവും, അല്ലെങ്കിൽ പ്രിൻറ്ററിൻ്റെ ഡിവൈസ് ക്യൂ, അല്ലെങ്കിൽ പ്ലോട്ടറിൻ്റെ ഡിവൈസ് ക്യൂ, അങ്ങനെ ഡിഫറെൻറ്റ് ക്യൂസ് ആർ ദർ. സോ വെൻ you want to read the data from the user, obviously it enters into the keyboard queue. Input output queue പറഞ്ഞാൽ different input output queue ഉണ്ട്, അതിൽ നിന്നുണ്ടായിട്ട് keyboard queue ലേക്ക് അത് പോയി. keyboard queue ലേക്ക് പോകുമ്പം when the keyboard is free, it enters into the input output device. When it is entering into the input device, it is now doing the operation, input output operation. ഇവിടെ ഇൻപുട്ട് ഓപ്പറേഷൻ ഞാൻ എന്താ എക്സാമ്പിൾ പറഞ്ഞത്? കീബോർഡിൽ സ്റ്റുഡൻറ്റിൻ്റെ നെയിമും റോൾ നമ്പറൊക്കെ ടൈപ്പ് ചെയ്യുന്നതാണ് നിങ്ങളുടെ ഓപ്പറേഷൻ. നൗ ഇതെല്ലാം ടൈപ്പ് ചെയ്തിട്ട് നിങ്ങൾ എന്താ ചെയ്യുക? എൻറ്റർ കീ പ്രസ് ചെയ്യും. വെൻ യു പ്രസ് ദി എൻറ്റർ കീ, ദാറ്റ് മീൻസ് ദ ഇൻപുട്ട് ഔട്ട്പുട്ട് ഓപ്പറേഷൻ ഇസ് കംപ്ലീറ്റഡ്. When the input output operation is completed, what the process will do? It will again enter into the ready queue. Right? So if it is the first process entering into the ready queue, obviously if the CPU is idle, again that process will be entering into the CPU. So it goes on like this. So whenever there is a input output operation, it comes into the input output device queue, and when the device is free, the process will be allocated to the device, and after the input output operation is completed, it again enters into the ready queue. Right? Now another case, in the CPU you are from the ready queue you allocate one process to the CPU. Second case, ഇവിടെ input output operation ആണ് ഒരു കേസ് ഞാൻ പറഞ്ഞത്. CPU എന്നുണ്ടായിട്ട് പുറത്ത് വരുന്ന കേസ്. Right? CPU എന്നുണ്ടായിട്ട് you are going to switch to another process. എപ്പോഴാണ് ഒരു പ്രോസസ്സിൽ ഇൻപുട്ട് ഔട്ട്പുട്ട് ഓപ്പറേഷൻ ഉണ്ടാവും, CPU will switch to another process. Another situation is if the time slice expired. Time sharing environment ആകുമ്പോൾ എന്താ ചെയ്യാന്ന് വെച്ചാൽ ഓരോരോ പ്രോസസ്സിനും 10 സെക്കൻഡ്സ് അല്ലെങ്കിൽ ഓരോരോ പ്രോസസ്സിനും 10 നാനോ സെക്കൻഡ്സ് എന്ന് പറഞ്ഞിട്ട് ഒരു ടൈം സ്ലോട്ട് വിൽ ബി അലക്കേറ്റഡ്. അപ്പോൾ ഫോർ എക്സാമ്പിൾ ഇഫ് 10 nanoseconds are over, 10 nanoseconds are over for that particular process, what happens after the 10 nanoseconds, the time slice is expired. So what it will do, it will again enter into the ready queue. അപ്പോൾ പ്രോസസ് 1 ഉണ്ട്, പ്രോസസ് 2 ഉണ്ട്, പ്രോസസ് 3 ഉണ്ട്. അപ്പോൾ 3 പ്രോസസ്സിനും എങ്ങനെയാണ് കൊടുക്കുക? 10 നാനോസെക്കൻഡ്സ് ഫോർ പ്രോസസ് 1, നെക്സ്റ്റ് 10 നാനോസെക്കൻഡ്സ് ഫോർ പ്രോസസ് 2, നെക്സ്റ്റ് 10 നാനോസെക്കൻഡ്സ് ഫോർ പ്രോസസ് 3. അപ്പോൾ വാട്ട് ദ സി പി യു വിൽ ഡു, ഫസ്റ്റ് 10 നാനോസെക്കൻഡ്സ് കഴിഞ്ഞ ഉടനെ പ്രോസസ് 1ന് ഇറ്റ് വിൽ ബി എൻറ്ററിങ് ഇൻ ടു ദിസ് പർട്ടിക്കുലർ ക്യൂ. ടൈം സ്ലൈസ് എക്സ്പയർ ആയി. So automatically from there it will enter into the ready queue. Then CPU will be executing process 2. Process 2 ന്റെ 10 seconds കഴിഞ്ഞാൽ again it will enter into the ready queue. Process 3 ന്റെ 10 seconds കഴിഞ്ഞാൽ again it will enter into the time slice expired queue. From there it will enter into the ready queue. So this is how it will be doing the second situation for switching from one process to another process. Okay. Now the third situation is, suppose say for example CPU is executing a process. ഒരു പ്രോസസ്സ് എക്സിക്യൂട്ട് ചെയ്തുകൊണ്ടിരിക്കുമ്പം ആ പ്രോസസ്സ് തന്നെ പുതിയതായിട്ട് ഒരു പ്രോസസ്സിനെ ക്രിയേറ്റ് ചെയ്യുന്നത്. ഇറ്റ് ഈസ് ക്രിയേറ്റിംഗ് എ ചൈൽഡ് പ്രോസസ്. ഇഫ് ഇറ്റ് ഈസ് ക്രിയേറ്റിംഗ് എ ചൈൽഡ് പ്രോസസ്, then what it will do, it will be creating a child process and the child process will be initiated. After initiating the child process, and the child process will now enter into the ready queue. So process 1, P1 is the process currently running. P1 is creating a child process. So now the child process will be initiated, so that process 1 as well as the child process will now enter into the ready queue. Or suppose fourth situation is, suppose CPU is executing the process, some other interrupt is coming in. ഞാൻ പറഞ്ഞിട്ടുണ്ടായിരുന്നു ഒരു എക്സാമ്പിൾ ഏർലിയർ ആയിട്ട് പറഞ്ഞിട്ടുണ്ടായിരുന്നു, ഒരു ഹയർ പ്രയോറിറ്റി പ്രോസസ് is coming in. അപ്പോൾ what happens, the current process will be interrupted. Or you have some keyboard key press event. So the key press event may be interrupting that particular process. Or print ചെയ്തുകൊണ്ട് നിൽക്കുമ്പം പ്രിൻ്ററിൻ്റെ പേപ്പർ ഈസ് ഓവർ, ദർ ഇസ് നോ മോർ പേപ്പർ ഇൻ ദ ട്രേ ഓഫ് ദ പ്രിൻ്റർ. പേപ്പർ ട്രേയിൽ പേപ്പർ ഇല്ല. അങ്ങനത്തെ ഒരു സിറ്റുവേഷൻ വരുമ്പം അഗെയിൻ വാട്ട് ഇറ്റ് വിൽ ഡു, ഇറ്റ് വിൽ ബി ഇൻറ്ററപ്റ്റിംഗ് ദ സി പി യു. അപ്പോൾ വാട്ട് ദ സി പി യു വിൽ ഹാസ് ടു ഡു, ദ സി പി യു ഹാസ് ടു ഹാൻഡിൽ ദാറ്റ് പർട്ടിക്കുലർ സിറ്റുവേഷൻ. സോ ഇറ്റ് വിൽ ബി preempting the currently running process and it will execute the interrupt service routine. So for which again whenever there is a interrupt occurring, it will enter into the interrupt queue and the interrupt will be handled now. So this interrupt will now enter into the ready queue, right? So this is a simple representation of how the process scheduling is done using the queuing mechanism. Okay, so this diagram shows how the process scheduling is done using the queuing technique. Okay, now when I was talking about all this process scheduling concept, one very important thing I was telling you is scheduling. So you need a separate module called as scheduler, which will be scheduling a process from the ready queue to the CPU. Now if you take a scheduler, the process will migrate among various queues. ഒരു queue ഉണ്ടായിരുന്നു, നമ്മളെ previous diagramൽ different queues are there. So the process will be switching from one queue to another queue, or I can say it is migrating or transformed into another queue during the life cycle of the process. And not only that, the operating system will select for scheduling purpose processes from these queues, correct? So the CPU is selecting a process only from these queues. So the operating system must select for scheduling purpose the processes from these queues in some fashion, and the selection process is now carried out by the scheduler, right? So the scheduler is the one which will be selecting the process from the queue to the CPU. Now if you take the scheduler, there are two types of scheduler. One is called as long-term scheduler, the other one is called as short-term scheduler. The long-term scheduler is otherwise known as job scheduler, and the short-term scheduler is otherwise known as CPU scheduler. And the long-term scheduler will select which process should be brought into the ready queue. So job queue nundayittu ready queue like konduverendadana long-term scheduler inde duty, right? What it will do, it selects the process from the job queue and it will put it into the ready queue, not to the CPU. So long term scheduler job queue lu nariya processes undu, adil nandayittu edengum oru process na based on the selection criteria it will select one process from the job queue to the ready queue. And the second one is a short term scheduler, which you call as the CPU scheduler. It selects which process should be executed next and allocates the CPU. That means what? From the ready queue, it will be selecting a process and it will be executed to the CPU. It will be allocated to the CPU. That is what is done by the short-term scheduler. So please observe here, the scheduling is done by short-term scheduler as well as the long-term scheduler. Long-term scheduler will select the processes from the job queue and it will be brought into the ready queue, whereas short-term scheduler selects the processes from the ready queue and it will be allocated to the CPU. So that is the role of these two schedulers, and these schedulers will follow some selection criteria. So based on the selection criteria only, it will take the data, it will take the process from the queue to the CPU or from one queue to another queue. Now if you take some operating system such as time sharing system, it will introduce an additional scheduler which you call as intermediate level of scheduling scheduler, is known as medium term scheduler, right? So some operating system will use the medium term scheduler also, and this is how it goes. The addition of medium term scheduling will be done using this. You have the CPU, you have input output wait queue, then the input output device, ready queue extra is available. Apart from that, the partially executed swapped out processes, right? So that will be stored in a separate queue which will be managed by the medium term scheduling. Okay, I repeat, some operating system such as time sharing system introduce an additional intermediate level of scheduling. This is known as medium term scheduler. So this is what is depicted in this particular diagram, and here in the medium term scheduler, that sometimes it can be advantageous to remove process from memory and thus reduce the degree of multi-programming. ചില സമയം നമ്മൾ എന്താ ചെയ്യേണ്ട, ഒരു 10 processes are running and all the 10 processes cannot be run concurrently. അപ്പോൾ what this system will do, the system will remove some process from the primary memory. So those partially executed process will be available in this particular queue. So the later the process will be reintroduced into the memory and its execution will be continued. And this scheme is what you call as swapping, right? So that is why we call it as partially executed swapped out processes. This will be managed by the medium term scheduler, right? So swapping in, swapping out. ഈ കേസിൽ എന്താണെന്ന് വെച്ചാൽ CPU we had seen already. Let me go to that particular diagram. CPU will preempt the process, right? So it will switch to another process in these 4 situations. ഈ 4 situationsലാണ് CPU വന്നിട്ട് ഒരു പ്രോസസ്സിനെ എന്നൊരു പ്രോസസ്സിലേക്ക് സ്വിച്ച് ഓവർ ചെയ്യുന്നത്, right? So by the time we are going to use only the long-term scheduler and the short-term scheduler. Okay. Whereas in some cases, especially in the time sharing environment, additional scheduler is also available, which you call as medium term scheduler. And this medium term scheduler, when it works, simply the CPU has lots of processes, around 10, 20 or 100 processes in the primary memory. By the time CPU thinks that, okay, let me not have all the 100 processes together, let me have only 90 processes. അപ്പോൾ എന്താ ചെയ്യുക, ബാക്കിയുള്ള 10 പ്രോസസ്സിനെയും എന്താ ചെയ്യേണ്ടത്, ഇറ്റ് ഹാസ് ടു സ്റ്റോർ ഇറ്റ് ഇൻ സം അതർ ക്യൂ. ബിക്കോസ് ഇൻപുട്ട് ഔട്ട്പുട്ട് ഡിവൈസ് ക്യൂലോ അല്ലെങ്കിൽ ചൈൽഡ് പ്രോസസ് ക്യൂലോ അല്ലെങ്കിൽ ഇൻട്രപ്റ്റ് ക്യൂലോ നമുക്ക് സ്റ്റോർ ചെയ്യാൻ പറ്റില്ല. വൈ? ബിക്കോസ് ഇങ്ങനത്തെ ഒരു സിറ്റുവേഷനിലും അല്ല നമ്മൾ ഈ 10 പ്രോസസ്സിനെ പുറത്തയക്കുന്നത്. സോ വാട്ട് വി ഡു, all these 10 processes will be entering into another queue called as medium term scheduler queue, where it is partially executed and it was swapped out by the primary memory, right? So this will be managed by the medium term scheduler. And whenever it is switching from or let me say, whenever it is swapping out the process and swapping it in the ready queue, this process is called as swapping, which is done by the medium term scheduler. Okay. So you have the long term scheduler, which will be, it executes less frequently. Why? Because job queue nundaittu ready queue like push cheynadu maatrana long term scheduler inde duty. So this will be executed less frequently, and this is the one that controls the degree of multiprogramming. Whereas if you take short term scheduler, it is invoked very frequently, because ഓരോരു ക്യൂ ഉണ്ടായിട്ട് ഓരോർക്ക് ഇൻറ്ററപ്റ്റ് വരുമ്പം ന്യൂ ചൈൽഡ് പ്രോസസ് ക്രിയേറ്റ് ചെയ്യുമ്പം അല്ലെങ്കിൽ ഇൻപുട്ട് ഔട്ട്പുട്ട് ഓപ്പറേഷൻ വരുമ്പം എഗെയിൻ ആൻഡ് എഗെയിൻ ഇറ്റ് ഈസ് ഗോയിങ് ടു സ്വിച്ച് ഫ്രം വൺ പ്രോസസ് ടു അനദർ പ്രോസസ്. സോ ദിസ് program or this module will be invoked frequently, whereas long term scheduler will be invoked very less frequently, right? But this is the one which controls the degree of multiprogramming, whereas short term scheduler is focusing on how frequently the CPU can switch from one process to another process. Okay. Now processes can be described as input output process or CPU bound process. Input output process will be spending more time doing the input output operation rather than the computations, right? So many short CPU burst will be available, because CPU instructions ഒന്നും ഉണ്ടാവില്ല, അതിൽ നിറയെ ഇൻപുട്ട് ഔട്ട്പുട്ട് ഓപ്പറേഷൻ. അതായത് യു ആർ ഗോയിങ് ടു റീഡ് ലോട്ട്സ് ഓഫ് ഡേറ്റ ആൻഡ് യു ആർ ഗോയിങ് ടു പ്രിന്റ് ദ ഡേറ്റ ഇൻ ടു ദി പ്രിന്റർ. അങ്ങനെ ഇല്ല ഒരു ചെറിയ പ്രോഗ്രാമാണ് നിങ്ങൾ എടുക്കുന്നുണ്ടെങ്കിൽ ദിസ് ഇസ് എ ഇൻപുട്ട് ഔട്ട്പുട്ട് ബൗണ്ട് പ്രോസസ്. Or if you have lots of executions, nariya expression calculate cheyyunnundu, ningal you are doing lots of computational work. Ipo numerical analysis program ella nokkittundeങ്കിൽ it is going to do lots of computational work. Angantha programs nella nammal endha paraya CPU bound process. So CPU burst or the cycle, CPU cycles will be very less in the case of input output bound process, and it will be very high in the case of CPU bound process. So based on this, if nariya input output bound process undengil CPU will be idle most of the time. Whereas if you have lots of CPU bound process, then obviously CPU will be utilized to the maximum. But you have to see that how the CPU bound process and the input output process should be balanced in such a way that the CPU utilization is maximized. So for which we do lots of context switching. CPU switches to another process and the system will save the state of the old process. We already seen nammal process control block inde samayathanne context switching padichittundaayirunnu. Context switching il we had seen that the state of the old process will be stored and the new process state will be loaded into the primary memory or into the process control block. Okay. And but if you see the context switch, ee context switch cheyyumbam switch cheyyunnu parnayinal oru process nundayittu ennoru process like it is going to switch, right? So from process 1 it goes to process 2. അപ്പോൾ what it has to do, CPU-ന് ഒരു overhead ഉണ്ട്. Overhead ഉണ്ട് പറഞ്ഞിട്ടുണ്ടെങ്കിൽ ഒരു another task it has to do. Apart from executing the process, what is the another task it is doing? It has to save the status of the old process. അപ്പോൾ ഇങ്ങനെ save ചെയ്യണമെങ്കിൽ again set of instructions to be executed. For loading the saved state, again some set of instructions are to be executed. So that is going to be the overhead for the CPU, and the system is not doing any useful work while switching, right? So because it is going to do only the saving and reloading, right? Saving the state of old process and loading the state of new process. So this has to be done again and again. So by the time it is not doing any useful work, and it is also time dependent on the hardware support. So ningala hardware inde capability, for example you have only 16-bit data transfer, or you have only 8-bit data transfer. appo angane very low bandwidth data transfer undengil obviously it is going to take lots of time. So context switching is obviously a time dependent task, but the time is completely depend on what kind of hardware support you have in the system, right? So these are the things that we should understand in the case of process scheduling. So next we will be talking about operations on processes in the next session.